Static equilibrium problems. Well, how do you solve them? That's the question that we're trying to look at today, and here's the very basic type of problem to look at. We have a plank, a seesaw, a teeter-totter. It is basically holding up two masses, a purple one and an orange one, and those two masses are actually located equal distance from the fulcrum, the place at which it pivots. Now, there's a couple of conditions that are going to be necessary for static equilibrium problems. First of all, we probably don't want the thing moving anywhere, so we're going to want to start with the idea that it's at rest. Now, the next conditions that need to be applied is we want rotational and translational equilibrium. Now, let's take a look at translational equilibrium. We're going to have to look at all the forces on the object, or I should say system, first. So here's the thing. We want to apply the forces at the points where their masses can be considered in one location. That's called the center of mass. That's what these little dots represent, as the center of mass of these objects, the plank, the two cubes. Now, when we draw the forces on these objects, the weight, because they have mass, are being pulled down by the earth, these three forces are pulling down. Now, that's not enough to put it into translational equilibrium. We're going to need at least one more force to make sure that the translational equilibrium, or the net force in the vertical direction, equals zero. And that force is supplied by the fulcrum. It's the support force. It has to equal the same amount of force as does the downward gravitational forces of all the parts of the system. So the fulcrum has to push up with that same amount of force. So now we have it drawn. It is in translational equilibrium. We do also want to realize that because it's actually arranged the way it is, with the two masses located where they are and where the fulcrum is located where it is, it's also in rotational equilibrium. Here's why. Because torque is actually calculated by taking the distance from the point of pivot, or the axis of rotation, to where the force is applied, and that force is applied in a perpendicular direction, then this force, if it's the same amount as this force, is going to wind up producing the same torque if they're located equal distances away from the fulcrum. So that's kind of how I set it up and said it was going to be done. And as a result, this thing meets both conditions of rotational and translational equilibrium. We could say it's in static equilibrium. Now, if we redraw it and we don't change how much mass is involved in this system, then we have a bit of a problem, because in this case, we are in fact in translational equilibrium. Our downward arrows of forces equal our upward fulcrum arrow of force as well. So the problem comes into the fact that that orange one is located a greater distance away from the pivot point, the fulcrum, than the purple. So the orange is going to produce a greater torque. And also the plank itself is going to be adding to that. So it's going to be lopsided. There is going to be a rotation that occurs in this system. It's not going to be rotationally in equilibrium. So that's a problem for us. Now, another problem that can occur for rotational equilibrium is what happens when we try to compensate for this and fix what's going on, and we wind up having a big mass so that the torque itself brings it back to rotational equilibrium. Well, then if you look at the arrows, we're no longer in translational equilibrium. We have more downward arrows and we do have upward arrows. So in order to get back to translational equilibrium, the fulcrum would actually have to be applying a force of equal magnitude. So that's kind of the conditions you'd be looking at, in which you have a rotational and translational equilibrium and how they'd work together to produce that static equilibrium that we're looking for so we could solve these problems. Now let's take a look at a very particular problem. Actually, before we do that, let's take a look at the definitions of these two. Rotational equilibrium, when the sum of all the torques on the system is equal to zero. Translational equilibrium, when the sum of all the force on the system equals zero. By the way, on translational equilibrium, there are two directions which force can act, so you want to make sure that the x and y axis are all in translational equilibrium. The steps involved for solving a static equilibrium problem? Well, fairly simple. You draw the problem, and you include the forces in your drawing. And then once you have your drawing down with all the forces applied and any angles that are in that drawing, you then go about writing your algebraic equations for the sum of forces acting on the system. And remember, it's in two coordinate systems, x and y. So you're probably going to have two sums. Then you write the algebraic equation for the sum of torque acting on the system. And the last thing you'd do is you'd use those equations you found, maybe all three, to try to solve for the variable you're looking for. Remember, you also want to include your units. Now, the classic physics problem is the ladder problem. Here's the idea. You have a ladder that's resting against the wall. This ladder has mass. And so there's a couple of different variations of the problem. One variation is there is no friction on the wall. The other one is there's no friction on the ground. Or there's maybe friction on both. And then you could also do something where someone or something is actually climbing the ladder. So the ladder problem itself has lots of different variations. We're just going to go through a very simple approach, which the wall has no friction and the ground does. Now the first thing we have to do is draw our forces. So as I said, the wall has no friction, it's frictionless, so there'd be no forces from friction there. Second, we draw the weight of the ladder. Now you notice the weight of the ladder is drawn to act at the very center of the ladder, and it goes straight down. Now that means it's basically half the length of the ladders where that force is located. The next force we draw is the fact that it's pushing down on the ground, so the ground would push back, Newton's third law. And the next force would be the fact that the ladder's also pushing against the wall, so the wall would push back. Don't get confused, this isn't frictional force. This is the force of the wall pushing back because it is being pushed by the ladder. The next force would be the frictional force we discussed. So that frictional force is going to want to prevent the ladder from slipping out sideways. So it pushes back towards the right. Now, the next thing we need to know is the angle, because there is angles involved, which, yes, that means there will be trig involved. Now, this angle looks to be about 50 degrees from the horizontal. So I'm going to go ahead and include that in my drawing. So we have all the information about our picture. We have our normal force down here, we have our weight, and we have our degrees. We also have the fact that it's a frictional surface, so we have the static force of friction. So the next step is to do the sum of forces. We're going to look first at the sum of forces in the x direction, or the horizontal direction. You can do the y first, it's up to you. First, we recognize that there's only two forces in this direction, the static force of friction and the normal force from the wall. Those two forces combined would wind up giving us a value of 0. It has to be 0 if it's going to be an equilibrium. If this thing doesn't equal 0, that means the ladder will be accelerating horizontally, and that could be a problem. So we want it to equal 0. We do the same thing vertically, and we find out that the normal force from the ground is counteracted by the weight of the ladder pulling down. Now, I know what you're thinking. They're not lined up. How could they possibly be counteracting each other? Well, it's the fact that we're looking at these forces in what direction they're in. It doesn't matter if that force is applied down here or up here. Wherever it's located, it's just a downward force against an upward force. And again, these forces have to wind up equaling 0 because we want it to be in static equilibrium, meaning there should be no net force, or translational equilibrium should be enacted. So the next step, which is more complicated, because now we have to do the sum of torques. Now to do this, we need an axis of rotation. We have to pick one, and it's really your choice. You could pick the center of the ladder to be the axis of rotation. You could pick 1/4 all the way up the ladder as the axis of rotation. You could pick the wall, as you can pick anywhere. Now, it would be wise to pick one that's going to reduce the amount of equations you have to deal with, that's going to get rid of anything you don't know. So pick a point that will allow you to avoid some more complicated math. Now, because there's really not a whole lot of math going on in this particular one, I'm just going to pick the bottom of the ladder as my point of rotation, my axis of rotation. Which means, by the way, all those forces located at that point don't matter. This is about torque, and those forces are at the point of rotation, which means there is no lever arm, which means lever arm times the force perpendicular, well, in that case would be 0. So that's why those forces went away, because there is no torque located at the axis of rotation. Next, I am left with two forces still left behind that are a distance away from that point. So my next step is I really want to get rid of all of the parts that aren't perpendicular. I just want the part of the weight that's perpendicular and the part of that normal force that's perpendicular. So I need to use this angle down here to figure out how much is going to be right there. Now, it's going to take a little bit of looking and trying to figure out what function you have to use. For example, if I want to use this angle, it actually turns out to be the angle that's located right here. Okay, so if I wanted to find out what this side was, I would consider that 50 degrees to be right here in that location. So in that case, I would wind up using a different function because it's on the opposite side. So as a reminder, this one's the angle next to it, so I'm going to use cosine. This angle right here would be this arrow. So if I move this right here, then that angle would be the arrow across. So that's the opposite. So that brings us to our actual equation. I take the weight times the cosine of 50 times half the length of the ladder, because that's the lever arm. Then I take that number and add it to the normal force times the sine of 50 times half the length of the ladder. Oh, it's not half the length of the ladder. It's actually the length of the ladder. Now, the reason why it's the length of the ladder is that's where that force is located. Now, there is one really tricky part. If I'm not paying attention, I might add those numbers together and it won't equal 0. The reason it has to equal 0 is because this torque right here has to be negative. And the reason why I said that torque is negative is because it's going in the clockwise direction. And anytime a rotation or a torque or any kind of thing dealing with rotation is in a clockwise direction, that's negative. If it's counterclockwise, like the normal force, that's considered positive. So that's how you find the sum of torque of that particular part. Now, once you know all three of these equations and how they relate, you could use this information to solve for, well, what's the coefficient of friction, or you could find out how much weight can be held. You can find a number of things dealing with the ladder problem in this way. Now, by the way, you could also apply this same idea to a non-ladder problem. For example, you can go back and apply it to the teeter-totter, because in that case, you could pick an axis of rotation. The weird thing is you don't have to pick the fulcrum. You just pick any axis you would like. Now realize if you don't pick the fulcrum in the case of a teeter-totter, you're going to be winding up adding an additional torque equation you have to include. So be careful about what axis of rotation you pick. That's how you do a static equilibrium problem. There's going to be lots of problems to practice in class, and so make sure you try those out with actual numbers. But there's the big idea behind it all. We're looking for static equilibrium.